Okay, yeah, so we're going to talk about graphs, knowledge graphs, so basically graph databases for RAG implementations. My name is David. Aside from all the stuff, I love to do AI, anything AI and ML. I actually do like a lot of AI ML on IoT Edge. I actually like to do a lot of vision, and I believe it or not, I actually build medical classification models for fun, so a whole bunch of fun stuff. Prior to that, I was in the Kubernetes and CNCF ecosystems, so we're doing like open source Kubernetes contributions. And then prior to that, I was in the backup recovery solution space, backing up virtualized environments, specifically VMware vSphere. So the agenda today, we're going to talk about, first kind of like the level set. I mean, when you hear about like RAG implementations, most people immediately go towards a vector database. So we're going to do like a little compare and contrast, and kind of the idea is pick the solution that best fits your use cases, right? And so we're just going to do kind of compare and contrast pros and cons between vector and graph, and then we're going to do a deep dive into, by example, into 3 key areas which I think graph databases for RAG implementations kind of really excel at. And the first one is like token prediction versus data relationships. The second one is explainable AI. And then the third one is leveraging basically the data within your graph databases for non-AI applications. And then we'll have hopefully some time for Q&A at the end here. So let's do a compare and contrast between vector and graph databases when it comes to RAG. So kind of even before that, there's graphs, vector, graph, NoSQL, oh my. There are a ton of different offerings out there to build RAG implementations off of, right? So you have all of the vector databases on the left, like Pinecone, Quadrant, Graph is like Nebula, Neo4j, and then you even have like NoSQL, SQL varieties, like Instacluster and PG Vector, which is like literally building vector databases on top of like traditional SQL, and even like in memory, like Redis, right? So there are a ton of different options. Definitely consider all of them when you go and you build a solution for your RAG implementation. So because vector databases have like a huge mind share, and like that's usually the first thing people gravitate towards, well, I'm just going to compare vector and graph, and then we can kind of take it from there. So what does a vector database do? What are the pros? So what vector databases really excel at is doing semantic search over unstructured text. When you're actually doing search and like trying to associate different concepts to each other, basically it's doing like next token prediction. You're moving from like one concept to the next. You're going basically through vectors. This word, then this word, then this word, and you're chaining them along. And when you're doing search in a vector database, you're doing a semantic search. So you're not searching for keywords, but you're actually searching for like the underlying concept behind the word. So like as an example, hot and cold might be temperature. So when you're doing queries in a vector database, you're not looking actually to say, hey, hot, and then the next token. It's more like the concept of like temperature. So I kind of want you to keep that in mind when you're thinking about how vector databases work. And because you're kind of abstracting the idea away from the words, that's how it's able to very quickly, efficiently, and scalably basically move from one concept to the next. Well, obviously accelerated by GPUs, but that's how it basically bites off doing the traversal in your vector database. And the other really great thing that vector databases excel at is it handles a diverse set of data types. So in this presentation, I'm only going to focus on text. But if your application's like multimodal, so you have image, you have audio, you have video, vector databases are great because, again, it's unstructured data. So now what are the drawbacks to vector databases? And this is kind of very interesting. Basically, the fundamental thing with vector databases, there is no relationship between data, between 2 sets of data. And the reason why is that these vectors exist as isolated vectors. You transition from one node to the next, and then there is no correlation between like how you make those transitions. Right? And so when you have that kind of a structure, transitioning from across one vector to the next, there's no way to see that a vector 3 things down the line might actually have a lot of relevance to what you're doing right now. And that is kind of like the Achilles heel, so to speak, for vector databases. And that's also the reason why when you do prompt engineering, you create a prompt for your query. That's the reason why you try to put chain of thought into your prompt, because you're giving it the breadcrumbs for your LLM and the embeddings that you're generating for a vector database. You're kind of like planting the seed so that it's able to try to make those associations in your query. And there's a bunch of other things that kind of like impact that as well, right? Top K, top P, which I'll actually go into in a little bit here. And so all of these different things that are meant to make vector databases excel and be very performant also hinder its ability to give you the appropriate or correct response. And this is kind of how you start to get into this weird hallucination territory. So, talked a little bit about vector databases. Let's go ahead and talk about graph databases and the pros. Graph databases, what they really excel at is presenting structured data and providing the relationships between different data nodes, so different pieces of data or information. And because it's structured and because there is an association made between 2 data points or 2 things, you can actually, and not only that, there's association between the next thing, the next thing, and the next thing. When you actually go ahead and you want to query and grab that information, you can actually grab all of that information in one shot, in the first shot. So that's why graph databases are kind of like really, really great at providing a response that's geared specifically towards your question or your prompt. The corollary to that is because you're actually grabbing all of the information up front and then passing it to the LLM, that's the reason why the hallucinations in a graph-based implementation are significantly reduced. Because you're effectively saying, here's all the data, give it to the LLM plus your prompt, and give me the answer. And so that's why you see in graph implementations, the hallucination rate is significantly lower. And because of that, you have a better response. Less hallucination, better response, more factual, right? So the cons. Now, the first word that I said in the pros category is also the cons. The problem is it's structured. You have to provide structure to the data that you're ingesting. And it's up to you on how that data gets structured and what that data looks like. So it's on you to manage the ontologies, the relationships between 2 different pieces of data or 2 different things. And in the demo that I'm going to show you in a little bit, I'm actually demoing taking a whole bunch of free-form text, kind of like to simulate like a vector database, using named entity recognition to pull out key features, pieces of information from the underlying data set, and using that to make the association to do the lookup for the query. But now it's on you to maintain those associations and those relationships. And then the other thing too is if you have frequently changing data, and you're updating that data really a lot, like really, really frequently, now it becomes even more difficult to keep that data consistency, right, update the relationships between your different sets of data points. So that's probably the most significant drawback to graph databases. But again, and also there's impacts to performance, right? Vector databases accelerated by GPUs are super, super fast. The trade-off in a vector database is that you take a performance hit, but you get a more precise and more accurate response that's not prone to hallucinations. And that's kind of the trade-off that you're making when you're deciding between whether or not you're using a vector database and a graph database for your RAG implementation. And then there are other databases that provide like in-memory cache or optimization, so definitely take a look at like Nebula. Nebula Graph, they're a graph implementation that provides like an in-memory caching layer to help like mitigate some of those, and do optimization so you don't take that much of a performance hit. But kind of like the thing is, you always get to pick one of 2 things, right? Really fast or like really correct. And so I kind of just have this architecture diagram right here. And the top is like a traditional RAG implementation based on a vector database, and then the bottom is a architecture diagram based on a graph database. And the biggest thing to note here, can you see my cursor, right? On the top, you see the kind of like 1 and 3. So you do the ingest on your data, it gets generated in embeddings into your graph or your vector database, and then your query comes in independent, goes through the embeddings and the LLM, and you get the answer. Now the bottom here, the way the graph implementation differs is you see that you generate the embeddings, so you basically store the information in a graph database, make the associations that you're going to make between however you want to do it, whatever structure you want to apply, and when you do the query, you actually get the data that's relevant to your query along with your query, and they go in together to the LLM, and that's the difference, right? You're basically providing all of the information to answer the question or the prompt up front, right? So now you're really restricted to that data set. Depending on how you do all your mappings and your configuration for the associations, you're providing all of that data, the correct data relevant to that thing, that question up front. So that's the difference between a vector and a graph database. Now, like the 3 topics that are kind of like, I kind of want to highlight and like do a demo on each one to kind of show you the difference. The first topic is tokens versus relationships. So doing token prediction versus data relationships. And let's go ahead and take a look at, first we're going to take a look at a vector, like traditional vector database, right? And when you're doing your next token prediction and you're trying to figure out what the next token is and the next token is, so we have one of the mechanisms to limit like what that next token is going to be is something called top K. So it's basically, top K is only consider the top K or top 3 or top 4 tokens in the response to the query or for the next token. So if we have this example sentence here, deep learning is vary, and then the LLM's chugging along trying to figure out what the next token is. And our top K is 3, which basically says we're only going to entertain the top 3 transitions to be able to go to the next token. The options are powerful, innovative, and complex. And the way that top K works, and this is again a very super simplified example, and there are other things like top P that help play some of this stuff out and help write it in a certain way. It just randomly in those top 3 decides to choose complex. And so now you can kind of start to see like some of the difficulties that come up with next token prediction, right? There's a certain amount of randomness and a variability when you're generating to get from one token to the next. So transitioning from one vector to the next vector to the next one. So what that looks like, if we actually kind of like to give you take that example and make it far more concrete. So the top on here, this top picture, if we had a top K of 10, and we have like she said, comma, quote, I never, and these are the top 10 tokens. And the problem with as an example for top K, like the optimizations for embeddings and LLMs where they're deciding how to transition to the next token, is that you have, these are the top 10 tokens, and then the little graph thingy next to the bar is kind of like the relative probability of that token being the correct one. And the problem with this top graph is that it gets cut off way too early because all of the probabilities for the next token are relatively the same. So that's to say that token 11, which isn't shown here, token 12, token 13, token 14, might also be an acceptable alternative for the next token. But because our top K equals 10, we're cutting it off at 10, right? And conversely, we might not cut off early enough. So if we still stick with that top K as 10, and we look at the sentence on the bottom, I ate the pizza while it was still, and it makes sense that it's hot, right? If you were to complete that sentence on your own, it probably wouldn't be I ate the pizza while it was still cold or warm, right? But probability-wise, the overwhelming majority the answer should, or the transition should be hot, but because we're doing K equals 10, it's gonna randomly pick out of that data set right there. So that's kind of just to show you although vector databases and next token prediction and all that stuff is very, very cool and awesome, this is how you can start to get into some of these little wonky territories and like with hallucinations and getting incorrect responses or responses that seem plausible but are not that correct. So how does a graph database improve that? On the left, you see, if we're starting from that little red dot and we're transitioning to the next token, which is that purplish dot, that's how a vector database would do. It would transition from one and land on the next token and find out what the weights are for the next vector on how to decide where to go. It moves into the next one, and then the next one, and then the next one. Now, the problem is if you needed information in the green dot, which is like 3 or 4 steps away, you're not going to get to that information till maybe never. And that's part of the problem, right? Now, in a graph implementation, because you're making all of the associations up front, you can grab all of the dots all at once and provide that as your input, as your starting point for your query or your prompt. And that's the difference, and that's the power between the two. So, instead of just talking about it, I'm going to go ahead and show it to you. So, I have an LLM running locally. It's Llama 3.3 on my laptop right here. So it's already running. I put a REST interface on top of it so we can query it. And then I also have my graph database of choice. I'm just using it for this demo as Neo4j. And I have already done the ingest of all my data. It takes a little bit of time, so that's the reason why I did it ahead of time. And so if we actually take a look at the database, you can actually see all of the things that are already populated. So here are all my entities. So I'm using a whole bunch of documents from the British Broadcasting Company, like news stories that I've basically obtained as my data set. And then I've done named entity recognition to basically pull entities or things out of the documents that are interesting that I think I could answer or query or do whatever. And so I basically pulled all of those entities out and made the association to the original document so that I can actually have the source of where that information or what reference that person, place, or thing, that's typically like a named entity, person, place, or thing, and to make that association so I can grab that original source data. So the question we're going to ask is, what do these articles say about Ernie Weiss? So that's the question that I'm going to query this LLM here. And if I go ahead and run the code, so this is the question that I asked. What do the articles say about Ernie Weiss? I'm using a named entity recognition library to pull out entities from that sentence or that question. And the entity that it discovered was Ernie Weiss. And it recognizes it as a person. Using the graph database, taking that named entity, and it's fetching all documentation relevant to Ernie Weiss that's contained in my graph database, because I have the ability, because graph databases, again, I can make the associations in any which way I decide. And this time in the structure for my graph database, I have entities pointing to the original documentation. The code queried the graph database. It found 2 documents that are relevant to Ernie Weiss. And it then took that information, and only that information, and provided an answer based on those documents. And you can actually see that the query was done. And so basically the text, generated text, the LLM consumed the documents, took my original prompt, fed it into the LLM, gave me an answer. We did a post 200, and that's the text that you see right here. You can understand how this could be far more precise than using a vector database when it comes to answering prompts and questions. It's because you're providing the context all up front instead of having to aimlessly or haphazardly transitioning from vector to vector to vector to vector, right? All right. So the next topic I want to talk about is explainable AI. And what is explainable AI? So explainable AI is basically makes AI decision making transparent and understandable. The problem with LLMs and the embeddings, vector databases and the embeddings that they house is that they're kind of a black box. There are definitely tools to help you understand how your prompt and like what answer you're going to get, but in general, they don't provide you like a fully transparent way to understand how that prompt is going to get answered and like what that answer is going to look like until you actually run it through, right? Because again, there's that weird variability where it can like say, I'm going to pick randomly from the top K3 tokens, right? So explainable AI uncovers how and why things get answers, the decisions get made by your LLM. And the goal for explainable AI is to do trust and validation and also to do bias and error detection. So you can uncover unconscious bias in your data, or you can find out that there's an error in your data. So this helps you do all of that. And because it's transparent and it's explainable, such as something that humans can understand, now we can interact with it, and it would be very hard for us as responses are flying by to answer a question because we're only seeing vectors, transitioning from one to the other. But in this particular case, because we're getting all of the information up front, it's something that we humans can consume and look at and understand. These things are associated to that. You can add, if you want, to put a human in the loop to understand like what is going on so that you know that the answer is correct because you can actually see the relevant information relating to your prompt or your query. And if you're interested in more about this, I actually have an NVIDIA GTC talk. I'm actually flying there tonight. It's a virtual talk. I'm going to post it. I can't post it, I think, legally this week, but next week I will post it on my own socials so that you don't need to have, like a virtual pass for NVIDIA GTC. You can look it up, or if you do have a pass, a virtual pass, you can look it up by that code S74147, or you can go to my YouTube page and I'll post the entire session, probably get in trouble for it. I'll post it there on YouTube so you can look, and it's like a 40-minute presentation equipped with demos on how explainable AI works and like what it means. Right, explainable AI, visualizing what your LLMs are doing, like how things are being answered, like how and why, right? So kind of like the takeaway is that graph databases offer like a contextual representation. Nodes and edges are nodes and associations. Because you can see those things in a graph database, you can make sense of like what is going on, like how the information is getting pulled and then being fed into your LLM. And because you can see it and visualize it, you can understand as a person like what is happening when these systems are chugging along and answering questions. And again, because you have a graph database and you can grab all of the information, you can do the same thing with a graph database with its own UI, which is what I'm going to show you next. Now vector databases, right, they're opaque, they're highly opaque, they're highly dimensional embeddings. So you have one node. If I just pick a random node in a vector database, that thing might have thousands and thousands of transitions to the next token with weights depending on what the prompt being fed into it and how those weights apply to that. So now you can kind of see it's very difficult to understand what is going on. So there are tools out there like Captum and Chap and all these other things where you can get insights to understanding how your prompt is getting answered. But if you look at all of those tools, and even some of the embedded tools on these vector databases, you literally have to feed in your question or your prompt, watch it kind of go through the vector database and as it's going from token to token to find out what your answer is. And because you have to do it in real time, like as it happens, that's kind of like one of the significant drawbacks for like making your data transparent and understanding how your question's going to get answered, and it's not explainable AI, right? You can't visualize the data and how it's going to be answered. So let's go ahead and go back to our Neo4j database, wherever the heck it is. So these are all, if I click here, these are all of the entities, at least the top 25, right? We did a limit 25 here. And these are all of the top top 25 limited entities. And if I go ahead, and I actually kind of knew where it was going to be. So this is our Ernie Weiss node, right? So this is where our node exists. And because we can actually click each one and like see, some of them are dates, right? So like what happened in 1973. But in our particular query that I demoed here earlier, this is the node that we're interested in, right? Because I said, who is this Ernie Weiss dude? And using named entity recognition, we were able to pull out that person's name, use that name to do queries for relationships. And so what that ends up looking like in code here, so the two documents that we saw right here, when we did our query, our RAG query, so we actually queried our LLM, it grabbed all of the information relating to Ernie Weiss in the documents, fed the documents plus our prompt, which is just a simple question, who's Ernie Weiss, feed it to our LLM and say, give me an answer. This is effectively what it did, right? Ernie Weiss, the two documents that basically reference this person, it took the text here and used that information to generate the answer. And because now you're kind of scoped to this, now you can see also visually, explainably, how the answer got generated, right? So this is kind of like one of the powerful things about graph databases. Let's see, oh yeah, go back to the presentation here. All right. And by the way, I have, as I'm demoing this, I actually have links here to I pre-recorded me doing this exact demo, so you can look back later on if you want. So the last thing, and this is kind of something that is really cool, is leveraging your graph database for non-AI applications. And I think this is a really cool example to really showcase why you should really consider, I don't have any stock in Neo4j or graph databases, right? I'm just showing you alternatives, right? But this is one of the reasons why you should really consider a graph database when you're looking at your RAG implementation. So let's just say we have an online store, right? You have an online store, you're selling widgets or whatever the heck it is you're selling. And you have, as a part of your online store, www.whatever, and you have a little chatbot in the corner. You can go up to the chatbot. He could be like an AI assistant, sales assistant to help your customers find the widget that they're interested in, blue, red, whatever. Because you're going to use a graph database, a RAG implementation with a graph database behind it with all the data stored in that graph database, when you start talking to your bot or your RAG agent, that information is all stored into everything about your online store is stored in that graph database. So this could be product info. This could be about user purchase history. It could be supply inventory. And so what's really interesting is that when you go and say, hey, or your user goes and chats with the chatbot and says, hey, I'm interested in buying this particular widget. Is this item in stock? And basically, you can have, depending on the structure, I would structure product as one category. So you'd have products, you'd have the association to its inventory. When the customer asks the question, is this particular item in stock? It's going to query the graph behind the scenes, right? Your RAG implementation is going to query the graph database, grab the inventory count, and come back and say, yes, we have 3 of these in stock, or no, we have 0, it's out of stock. And what makes that possible is because you have that data in a graph database. And you can see also, because you're grabbing that information, providing it to the LLM, it's very difficult for the LLM to screw up, because it's literally being told, we have 10 of these items in stock. Take that piece of information plus the question, you should get an answer of, we have X number of items in stock. So again, significantly reducing hallucinations in the answers to your LLM, right, and your RAG agent. Now, the more traditional side of the house for your retail or your online store is that you can use that graph database and all of the data that's contained within it to run traditional types of things. So this could be everything from like inventory management. This could be like sales reporting tools, right? Dashboards on like warehouse orders, right? And you can effectively, if you have, whether it's online or not, or a dashboard, whatever it is, you can query your graph database independently of an LLM and generate reports and do all sorts of things. And what I'm basically kind of describing here is that you have like now a single source of truth, right? If a customer buys one of the widgets, the inventory count gets decremented. The next customer comes in and says, how many do you have in stock? It's going to go into the graph database and grab the inventory. That inventory is going to be updated minus the one where the customer purchased ahead of them, right? And so that's really cool. You have a single source of truth for all of your data, whether it's for an LLM or whether it's for like a traditional app or reporting tool or whatever it is. So all your conventional business stuff is all taken care of as well. So I know this is probably the most anticlimactic part of the demo. I'm just going to query using Neo4j's, basically its API, so that I can just get that data independent of the LLM, which I'm going to shut down right now. So it's not running anymore. Python, I think I called it standalone, and basically passed in Ernie Weiss, got the two documents that were associated with it. And it could be anything, right? It could be, like I said, product or inventory for this particular product. Here's the inventory for it, right? And just basically to show you that you can still do it independently of an LLM or an AI system. Vector versus graph, key takeaways here. Find the right tool that's right for your use case. Like, you always hear, do the due diligence, definitely evaluate all the different options that are out there, even the ones that I didn't cover today, right? It's like some of these other ones like Redis, which you can do graph in memory, right? And there are reasons for wanting to do that. But in this particular case, graph databases, some of them are accelerated by GPUs, which are interesting. But most of them are CPU optimized. And CPU optimized is another way of saying like, hey, yeah, you need to like ingest all of your data, apply structure to it, and ingest it and put it into your graph database. But the cool thing is because it doesn't require any special hardware, you can distribute the ingest across all of the CPUs that you need in your Neo4j cluster or whatever, right? And then likewise on a vector database, for it to be actually performant, you need a GPU to be associated with that vector database. The ingest and embeddings take time. Like if you have a huge amount of data, right, you're going to need like an H100 or whatever to ingest a crap ton of data into your vector database. Once the ingest happens, you can probably scale it down, use a less performant GPU for inference, but you still need that, right? And then, like I said, vector databases are quick scalable, especially if you're doing multimodal type stuff, image, audio, video. So, resources. So the top link, right here, click it. I'm going to tweet my slide deck out afterwards. Top link contains the link to my GitHub, which literally contains all of the code and a README on how to do all aspects of the demo that I just showed you right here today. If you're going to use a vector database and you're going to train, in DigitalOcean, we're a cloud provider. We have GPUs. Train your vector databases on DigitalOcean. And if you're going to use a graph database, we also do normal, traditional, non-GPU workloads in the cloud as well. If you want to keep talking about it and continue the conversation, DigitalOcean, you can go visit our Discord here. Here are three, I think, really cool, different. They all have different variations of like why they're interesting. But here are three different graph database options. And then the data set I also used in the demo here for today. And that will be it. Actually running out of time. I think we have time for maybe one or two questions.